Once we've streamlined the math of training, another bottleneck quickly emerges: the hardware itself. Today's data centers are constrained by how machines communicate. Copper links are power efficient, but can only reach a couple of meters, while optical links extend farther, but burn far more power and are less reliable. That trade-off limits how we design and scale AI clusters. To explore a new path forward, let's hop across the ocean to our Cambridge lab, where Paolo, a senior principal research manager, is rethinking data center hardware with some very cool micro-LEDs. This breakthrough has the potential to rethink AI data center design and open the door to new possibilities in scaling.
Hi, I'm Paolo Costa from Microsoft Research in Cambridge, in the UK. And today I would like to talk to you about how we can reimagine the next generation infrastructure using microLEDs. So the trend where we're seeing across many generations of AI accelerators is that while the compute has been able to scale at a reasonable pace, the network and the memory have been lagging behind. And indeed what we are seeing is that AI workloads, especially inference ones, are becoming I/O bound. What it means is that we cannot fully utilize our GPUs because they are bottlenecked on either the memory or the network or both. One of the key reasons for this trend is that today's communication technologies force you to make a tough choice. On the one hand, you can use optical communication with lasers. You can have very long reach, like tens, 100 meters and beyond, but the cost and power is very high. And also reliability is very low. And so whenever you can, you're forced to use copper cables, where are very low cost, extremely low power, and highly reliable, but the reach is very short. In fact, it's less than 2 meters for GPU to GPU, and only a few millimeters for GPU to memory. And this is actually creating a number of challenges for system designers. For example, recently NVIDIA introduces the latest Blackwell rack, where you have 72 GPUs just inside one rack. This is 120 kilowatt per rack, or the equivalent of 60 dishwashers. And projections for future generation is to go beyond 0.5 megawatt per rack. And the only reason you have to put so many GPUs inside a single rack is because you're forced to use copper for their high bandwidth connectivity, multiple terabits per GPU. But as you can imagine, this is becoming extremely challenging from a cooling, thermal, and mechanical standpoint. And ultimately, this is limit the number of GPUs that you can interconnect at high bandwidth. Similarly, for the memory, since we can have only put the memory next to the GPUs, there is only so much real estate that you can use. And so again, this is constraining the amount of memory that you can make available to each GPU. So why is optics so high cost and high power? The reason is because today we use lasers that are extremely expensive, they are very high power hungry, and so in order to amortize their cost and power, we have to transmit faster and faster. We used to do 25 gigabit and 50 gigabit, and now we do 100 gigabit per channel. Next generation is going to be 200 gigabit per channel. So for example, today in one transceiver we have 8 lasers, each one transmitting 100 gigabit. However, as we go up in speed, you need more and more complex electronics to compensate for transmission impairments. And this also adds up to the power and also the cost, because you have to use the latest CMOS processing node technology like 5 nanometer or 3 nanometer in the next generation. Also, since lasers are operating in the infrared region of the space, you cannot use silicon photodetector, you have to use more complex materials like silicon germanium or gallium arsenide. And this is where the high power and high cost comes to the picture. And also, when you operate at such high speed, margins become smaller and smaller, and this also ultimately leads to higher failure rate. So, in our approach, we decide to go to the completely opposite direction. Rather than having a few channels operating at very high speed, we adopt a wide and slow architecture, which means having many channels, each one operating at very low speed. So, for example, to get to the 800 gigabit, rather than having 8 channels at 100 gigabit, we can have 400 channels, each one operating at 2 gigabit. The advantage is that now, since we operate at very low speed, the electronics become much more efficient, We don't need to use advanced signal processing. We can do anything in the analog domain, and we can also relax the requirement in terms of processor node size. Now, we can't use lasers because this would just break the bank. So instead we use microLEDs. MicroLEDs are very similar to the LEDs, for example, that we have in this room, but are much smaller, like 5-10 micron size. And this is a technology that is being developed for next generation displays, like smartwatches or head-mounted devices. And they provide three advantages. The first one is that they're extremely cost-effective. Second, they can operate at very, very low power. And also they're very small, and so what it means is that you can pack many of them inside a single space. Also, they operate in the visible range, like green, blue, red. Why is this important? Because now on the receiving side, we can just use a standard camera sensor detector like the one that we have in our phone. And so when you combine all of this together, what you're seeing is that we can get very low cost and very low power. Also, since we can put many of them in a very small space and they're very low power and cost effective, it's easy to over-provision them, which also makes them much more reliable. Now, I make it sound like very simple, but actually realizing this vision in practice requires a lot of innovation across the stack, and also require a very multidisciplinary team with expertise across many fields, from integrated photonics, material science, lens design, and digital and analog design. So one of the first challenges we had to solve is how to make these microLEDs that are designed for very slow rate to operate them very, very fast. But also, we have to look across the stack. For example, we design new type of optics that allow to better couple the light into the fiber. Also, we don't use standard fiber, we use imaging fibers with thousands of cores. This is a fiber typically used for medical applications, like endoscopy, and instead we use that for communication. And also we've been looking at beyond the single module, for example, looking at designing new connectors and optical circuit switch that are compatible with these new technologies. Now, we really have great support both from Microsoft Research and from the Azure team. And together with our supplier, we were able actually to demonstrate that it's possible to build a technology that breaks this trade-off. So we can have at the same time low power, low cost, and high reliability, while still having a reach of up to 50 meters. And one of the strengths of this technology is that it's fully compatible with today's form factor. And so what it means is that it doesn't require any changes to existing switches or NICs and can be immediately deployed. Also, since operated at the physical layer, it's completely agnostic to the protocol. So you can use it for Ethernet, CXL, PCI, and so on. This is already a big win because it can address today's pain point. But what makes me excited is the fact that it can also open up new exciting opportunities as we think of the next generation AI infrastructure. For example, on the networking front, since now we are not constrained by the short distance of copper cables, we can now expand the high bandwidth domain to multiple racks. And also we can use more flexible topologies, for example, using optical circuit switch, which will improve our efficiency and overall utilization. Also on the memory front, we are not constrained to put the memory next to the GPU, but we can now disaggregate the memory, but removing the memory off the package, which would allow to increase the memory bandwidth and capacity that is available to a GPU, but also make it possible to explore novel type of memory that are different from the one that we use today. And finally, and this is really our North Star, would be the idea actually to put the microLED directly on top of the GPU, because this can unlock the full areal bandwidth. Now, this would require a lot more innovation happening at the packaging side and thermal and microLED devices. But if we can get there, this can really be a game changer, because this can enable to have multiple of petabits of bandwidth coming out from the GPU. And so what we really would like to do is to engage with the broader research and the industry community to work together, understanding how we can best leverage this property and design together the next generation AI infrastructure. So, thanks so much for your time, and looking forward to connect to all of you.